Go on. Let's start recording. I hope it's starting. Right. Okay. Good morning. Week 8. I'm going to carry on with unsymmetrical shear example. And then we are going to do something mind-boggling, challenging, but it's the real stuff. Okay. Combined loading. Term test 2, March 14. Okay. 7 a.m. My 9:30 got double zeros. Okay. It's going to be face-to-face. I already booked the room. We are going to be in Peter George building, okay, the big one over there. Okay. How many questions? I don't know yet. Whether is it open book? I think I don't know yet. Okay. I'll let the time go further. Then we decide. Maybe next week we can decide. Okay. Right. So today we're going to continue on our example. I still remember last Friday before reading week, I messed up so much. Okay. I hope not to be the same. So what I'm going to carry on this example is we're going to determine we have already located the shear center. Okay. So just to recap, the formula we're going to apply is equal to the shear stress is equal to VQ over IT. Right? And in order to apply this formula, we have to ensure there is no twisting deformation during loading. Okay, just to recap. So if we were to construct our centroid, okay, I'm just going to sketch our centroid. Okay, there's our centroid in the vertical, and then the centroid on the horizontal. Okay, so if I call this left-hand side and right-hand side, we realize that the right-hand side structure is less what? Rigid. Right? Some of you say, Eugene, why less rigid? We know that second moment of area I is equal to BD cubed over 12. Right? On the left-hand side, look at the D. Bloody hell, look at this. Right? You have a very high depth geometry to resist the what? Twisting. So that's why the right-hand side is less rigid than the left-hand side. So the structure will twist. So in order to apply this formula, we need to determine the shear center. Which is over there, our O. And we found our distance O on our last lecture. Okay. So where I want to continue is we are going to look at the distribution. Okay, we're going to find the distribution of the shear stress caused by the shearing force and apply at O. Okay, O means it's at a shear center where it's applied at O. There is no what? Twisting. Okay, twisting is equal to 0. Okay, so I will erase this. Okay, we will start from the very. I'll write everything out in case we forgot. So we're going to find the shearing stress distribution. Okay, stress A, stress B, stress at point A, point B, point D, point E, point F, and point G. Okay, and we realize that at the terminus. So where are terminus? So the terminus are the dots that I'm drawing over in black now. Our terminus over there, the shearing stress are equal to 0. Okay, because our first moment of area is equal to 0. Okay, so we know that shear stress at point A, shear stress at point D, shear stress at point F, shear stress at point G, they are all equal to 0 because the first moment of area is equal to what? 0. And they are at its terminal. Okay. Okay, well, I'm going to start from there. Okay, carry on from. So now we are going to find at point B. Now, point B, there are different locations. Okay, let me describe what do I mean by different location. So I'm going to sketch point B up. So we have this, this. Okay, so I think I'm going to sketch our centroid. Okay, so this is our centroid. So this is our point B. Okay, but point B have different location. Okay, we have point B at here. Okay, so this is point B. Just by looking at the flange over here, point B of the web. Okay, and then when we come over here, is point B, right, at the web plus flange. Okay, so three different locations. In geometry wise, I did not touch this the last time I taught this. I do apologize. In terms of geometry wise, what do we see? Okay, in terms of geometry wise, we see this. Okay, so the distance given to us, right? The distance from, let me draw our centroid first. So what we are given, the distance from here to here is 3, right? The distance from here to here is 4 inches. And the distance from here to here is 2 inches. So why I draw that? Because we only take the center line, okay, in thin wall unsymmetry analysis, okay? We only take the center line. So this thin wall, we know that the thickness, what's wrong with me, is equal to 1/8 of an inch, okay? So now we are going to find the Q. Okay, we're going to find the Q of the flange, or Q point B. Hey, come on, Eugene. Okay, flange. And this is also the same as point E, okay, flange. So width is equal to 4. So flange is this region, okay? I will color this region. So this is the area we have to consider. So the width is 4. The depth is 1/8. The y is 3. Okay. So this is 4, 1/8 is equal to 3/2 inches cubed. Okay. So directly we can find out that our shear stress at point B, the flange, is equal to shear stress at point E at the flange. So this will be equal to the, so we know that the shear, the V is 2.75 times 10 to the power 3. Okay. The Q is 3/2. Okay, so if you look back at the value that we get for our I is 233/12. And this is thickness is 1/8. Okay. So 2.75 over 3 times by 3/2 divided by 233 over 12 divided by 1/8. I get 1.7 or 1,700 psi. Okay. So I'm going to do another point. Okay, we're going to do Q at point B. Okay, for the web. It's also the same as Q at point E, okay, for the web. So this is equal to the width is 1/8 now. Okay, now when I take the geometry, I use this diagram over here for the geometry. Okay, so I will shade the area of concern now is this area over here. Okay, so width 1/8, the depth is 2, the y bar is 3 plus by 2 divided by 2. Okay. So this will be equal to 4 times 2 times 1/8 is equal to 1. So likewise, you apply the formula. Shear stress at point B of the web is equal to shear stress at point E at the web. So this will be equal to 2.75 times 3 multiplied by 1 divided by 233 over 12, 1/8. So 2.75 power of 3 divided by 233 over 12 divided by 1/8 is equal to 1.133 or 1133 psi. Okay. Then we are going to look at point B. Okay. We're going to look at point B with the web and the flange. Okay, so I think you all get the idea now. So I'm going to do point B. Okay, so no, sorry, I'm going to find Q at point B, the web plus flange. Okay, now my dilemma in this problem is this. Let me write the next one first. So this is also equal to Q point E, the web plus flange. Okay. So if you look at the diagram on the left, where I highlight the area, right? If this was thick wall, right? You have to consider this area. You get what I mean? Right? But because it's thin wall analysis, right? All we need to do is this. Okay. So all we need to take is Q at point B for the web plus by Q of point B of the flange. Some people might say, Eugene, why is that? Because 1/8 multiplied by 1/8 is very what? Small. Yes or no? Right? So that's all we need to do now. So this is 3/2, or this is 1 plus by 3/2. So it's equal to, I don't need a calculator for this, come on. I do, okay? It's equal to 5/2. Okay? And why I say we ignore the orange area, if we were to take the orange area into consideration, okay? So you have 1/8 multiplied by 1/8 multiplied by 3. All right, so 1/8 multiplied by 1/8 multiplied by 3, you have 3/64. Okay, oh, this is so bad, sorry. So this value is very what? Small. Okay? That's why we did not consider it. Okay? Compared to 5/2. So 5/2 divided by 3/64.